In this video, we're talking multiplication rule and independent events, a definition for you. So we got a rule, we got a definition. Let's get into it. The definition is what's going to lead us into the multiplication rule. Throughout this video, we're going to be talking about and using some terminology, so I want to make sure we're on a clear page here. So this is my little note to you, that when you see with replacement, the whole idea of this with replacement note is to just denote, for instance, if we're picking marbles from a bag, if I'm picking, let's say, 3 marbles, if I keep picking one out, making an observation, putting it back in, we'll call that with replacement, meaning that every time I interact with this bag, it's afresh every time. With replacement is a nice convention. Not often the case, but certainly for these first few examples, that's the way that we'll talk about these probabilities. What is independence? We have 2 events, let's say E and F. They're independent if the knowledge of one has no influence, does not influence the probability of the other one happening. The classic example of independence is when you have replacement, that every time you reach in that bag of marbles and you look at it, okay, then you put it back in and it's afresh. I have a little example about flipping a coin, right? When you flip a coin, it lands up heads. The fact that it lands up heads has no bearing on you taking that coin, flipping it again, and it landing on heads or tails the next time. So those 2 events, heads and heads, are considered independent events. I have some little reminders up top that we'll use. I'll reference them throughout. The one that I'll mention, mostly because it's fundamental for us, is that, look, whenever we're talking probability, we should always think probability of some event occurring is equal to fraction. That should be number that we want up top, divided by how big our space is down below. We'll use that quite a bit. We'll also use this at least one, think 1 minus none business as well, but that'll be included in the example that we get to. Let's dive into our first real definition and what we can do with these independents. Let me also see if I can, there we go, slide over here. So we have 2 events are independent. There's actually a great rule that we can get, that we can take something that's very complex and separate it into smaller components. Take a big problem and make it into a couple smaller problems. In fact, we have a nice formula here. It says, look, if events E and F are independent, I actually get a very nice formula. It looks like this: probability of E and F, again, and think multiply, but there's an important that this is only true if things are independent. Then and multiply, much like our addition rule we talked about in the past, I can separate these and look at them on their own. That's the probability of E multiplied by times the probability of F, which is why you read and, we think multiply. But again, this formula only works if those 2 events are independent, so it's important to keep that in mind. We'll get some more formulas in the future with a general multiplication rule, so we'll talk about that later. So this multiplication true is true for just 2 events. If 2 events are independent, it's also true for n independent events, and that's what this little rule basically says, that if you have 1, 2, 3, 4, 5, n events, then I can separate it, again, provided if they're independent, to the first event times the second event times the third event. And so we can take this big complicated problem looking at all these things happening, and instead of looking at this massive event, I can break it down into smaller components. A classic example is, let's say I'm rolling a dice 2 times. Well, instead of me looking at these 2 results, since me picking up a dice and rolling it is independent, right? I start afresh every time. Well, instead of me looking at these 2 rolls as a sum, I can separate and look at each roll independently of each other. And so that's the beauty of this independence rule. As a little note to self here, little recall, let me make sure I'm out of the way here. We talked earlier about mutually exclusive, and sometimes mutually exclusive and independent get confused, and so I want to make sure to highlight the difference between the 2. Mutually exclusive, if you remember, is when things can't happen together, or simultaneously was the word that we use. And so think about that as me having 2 dice and rolling them, or me taking 1 dice at a time and rolling it, and then rolling it again. Simultaneously versus in consequence, or one happening after the other, which is independent. We think of things happening in sequence. So it's important to make that distinction there. Assume that a study by human resources has found that the probabilities of an employee being written up for certain infractions are the value shown in the following table. And so here we have, for instance, an infraction of being insubordinate. And it looks like pretty likely these infractions, again, of all the infractions, about 14% of infractions are for employees being insubordinate. Our task, assume that each infraction is independent of the others. This is going to be an important thing, so I'll circle it, independent. what is the probability that a given employee would be written up for being late for work, taking unauthorized breaks, and leaving early? My goodness, this employee's getting written up a bunch, all three things. Well, let's see. We can first start off with defining, right? They said probability. So let me write out what the event is, probability of. Let me write LW for being late for work. That's my first infraction. And taking unauthorized breaks, or TUB for short. And then lastly, and the third one is leaving early, or LEE for short. So these are my three infractions. So normally what I'd have to do is think about all these infractions lining up. Of all the three infractions that exist, what's the probability that this one occurs? This is a very complicated event. But fortunately, we make the association that whenever you see and, we should think multiply. But there's almost like a little asterisk that we need to think about. Multiply, yes, but we need to be very careful if, I'll just write IDN for independent. We need to be very cautious if these are independent. Fortunately for us, big check mark, whoop, it's in the question. It says these infractions are independent. So of course we can separate into multiplication. I'll do the first one. Probability that we're late for work is the first infraction. Multiplication, here's the beauty, times probability that TUB, somebody's taking unauthorized breaks. There's my second infraction, times the third one, probability that somebody is leaving early. There's my third infraction. So again, the beauty of this multiplication rule is I don't have to worry about this very complicated, making all these infractions. When you see and, think multiply, and then with a little asterisk, because we need to think only if this is independent, I can separate this complicated event into three smaller ones. And so now this is an exercise of simply reading our table. The first one, late for work, it looks like has a probability of 0.2478. Looks like pretty likely a quarter of individuals. I'm going to then multiply that by taking unauthorized breaks. I can look up, barely covering that one, at 0.3186. Again, multiply by my last one, leaving early. It's going to be down here at 0.1954. And again, these are all being multiplied together. So type the first one in times the second times the third, all my infractions multiplied together. I cheated, I did it beforehand. The probability should be 0.0154. And that's the probability that we're interested in. Again, if it's helpful, we should think about this as a percentage. Move this decimal over 1, 2. That's going to be 1.54% or 1.5%. So what's the probability that somebody makes all these three infractions, late for work, taking unauthorized breaks, and leaving early? Not very likely. And so if you do have that employee, right, they're a cut above the rest, very unlikely that these three infractions are going to be paired together. Next example, on a 5-day vacation, the forecast is a 20% chance of rain on every single day. So when we hear 5-day vacation, forecast 20% chance of rain on every day, we want to know what is the probability that it rains every day. It's important when we think about this that we understand the experiment that's at play here. It says we're on a 5-day vacation every day. And so I need to think about this as almost like 5 slots to be filled. That's my first day, second day, third day, fourth day, and fifth day, where these are slots to be filled. I can think about them as events, each one to be filled. And I want to know the probability that rains every day. Let me first start by starting off, what are they talking about? Let's write out the event. That should be the probability that it's going to rain on the first day. So I'll write R for short. Rain on the second day. 1, 2. Rain on the third day. Rain on the fourth day. My goodness. Okay, still going. And rain on the fifth day. That it's going to rain every single day. And so before I move on, I can look at all of this whole week. It's a big, complicated event that it's going to do all these things. I need to consider raining every day, raining 4 days, 3 days, 2 days, 1 day. There's all these different outcomes that can exist. But the beauty is, again, whenever you see and, we should be thinking, I know what this is. This is going to be multiplication, but only if independent. That every single day has this same probability, not related to the other. Notice up top it says the forecast is 20% chance of rain every day, meaning these are all independent and the same. Notice up top it says the forecast is 20% chance of rain every day, meaning, yeah, these things are independent. Notice up top it says the forecast is 20% chance of rain every day, meaning this 20% chance is independent every time. And so now we have the power. I know it's independent, so I can write this instead of looking at a big event. I can look at this as 5 separate smaller events. So this should be the probability that it rains on the first day times probability that it rains on the second day times probability that it rains on the third times probability that it rains on the fourth times the probability that it rains on the 5th day. I can multiply all of these independently on their own. I don't have to look at this as a big event. And so I actually know the probability that it's going to rain on any particular day. That's this 20%. So it should be 0.2 times 0.2 times 0.2 times 0.2 times 0.2. We have 5 of those. 0.2 times 0.2 times 0.2 times 0.2 times 0.2. What a tongue twister. So if I want to find my probability, I can either just multiply that through. For any of you math people, there's actually a fun little trick, a more efficient way to do this instead of typing all those numbers in. That if you're multiplying the same number by over and over, this is actually what exponents are for, what powers are for. So I can write this as 0.2, little caret here, to the 5th power, or raised to the 5th power. And if you do that, you'll get the same answer as you multiply them all together. And the multiplication should give you 0.0003. Highly, highly unlikely, right? Which hopefully is a good thing, right? If we're playing this vacation and you hear 20% chance of rain, you're like, we're never going to get outside. But when you look at that, if things are independent, the probability that it's going to rain every single day, not likely. And hopefully that's something that gives us assurance. But maybe we're interested in a different perspective. What is the probability that it rains at least one day? I have a little table here we'll use to answer this question. Probability at least one day. Let me write it like this. We'll write probability of, and it says at least one day. Or you can put at least one R to keep with our rain on every day. So I'm looking at least one rain. Let me slide over here just a bit and we can look at my table we have above. This at least one, well, that would be like one day would be good. That's what I want. At least one day. 2 days would also be good. 3, yes. 4, yes. 5. In fact, at least one day references all these things. This is like what I want. Some of you maybe know where I'm going with this. We have a nice key or rule to think of, and it looks like right here, I'll box it for us. It says, look, if ever you're doing the probability of at least one, think 1 minus none. It's much more friendly. And so as we talked about in the past, if I want all those things, I can find the probability, but I'd have to add these up because it's 1 day or 2 days or 3 days, or this is a lot of probability. You're going to have to add up all of these separate events together. We don't want to do that. Instead, I can think of, well, what's the complement? It's what I want complement, the opposite of that, which is it raining no days. And so instead of me finding the probability directly, at least one rain day, let me find it indirectly. 1 minus the probability that I get no rain. 1 minus none rain, right? The grammar doesn't fit, but 1 minus none, I'll stay true to it. No rain or none are. So this is the rule. So when I go through, now let me figure out what's the probability that it doesn't rain at all. And here's how we'll break this up. Equals, all right, this says 1 minus. Let me think about what that looks like for this 5-day vacation, what it looks like to not rain on the first day, not rain on the second day, not rain on the third, on the fourth, on the fifth. Well, I can write this on each individual day. Again, 1, 2, 3, 4, and 5. Well, on the first day, it doesn't rain. I can think about that. Some of you might know the probability that it's not going to rain. If there's a 20% chance that it's going to rain, that would be an 80% chance it's not going to rain. But how would I express that? I'd express that as rain complement, that it doesn't rain on the first day. For the second day, rain complement. It does not rain on the second day, and so on and so forth. For the 4th day and on the 5th day, rain complement. There's a very important reason why I don't write the and character, because the second we see and, right, first day, second day, 3rd day, 4th day, and 5th day, I'm thinking multiplication, again with a star, have to, and I'll write it over here. If independent, I can break up that probability. This one is just chilling. We're not messing with it yet, but we are going to mess with this probability that it doesn't rain. So because they're independent, I can look at them individually on their own right. That should be the probability that it doesn't rain times the probability that it doesn't rain on the second day times the probability it doesn't rain on the third day times the probability it doesn't rain on the fourth day, and lastly times the probability it doesn't rain on the fifth day. These all things are being multiplied together. 1 is still just chilling, but I can certainly write my probability here. That should be 1 minus, again, the probability it doesn't rain is 1 minus this 20%, and so we'll get our 80%. 0.8, there's an 80% chance that it's not going to rain on the first day, times 0.8 for the second day, times 0.8 for the third, times 0.8 for the fourth, times 0.8 for the fifth. Whew! If you'd like to, you can get a calculator out and you can just simply multiply all those together. Let me do it like this though. Equals 1 minus, just like I talked about up top, instead of multiplying 0.8 times 0.8 times 0.85 times, you can raise it to an exponent to the fifth power because we're doing it 5 times. So 1 minus 0.8 to raise to the fifth power, little caret is how we get there. This should equal 0.6723. Like I said, I cheated, did it beforehand, and that's what we should get here. So again, the probability it's going to rain every day, don't count on it. It's not likely. Not even a full percentage. It's 0.003. But the probability that it's going to rain at least one day, well, you can add up all of these different events, finding the probability. It's quite tedious. Or we can do it the complement way, and we find there's roughly a 67% chance that it's going to rain at least one day. Again, it might rain one day, no big deal. It might rain 5 days. That would be terrible. And if you add up all those, if you add up all these different probabilities, you'll get 67.23%. This is one of the most fundamental independent events, and that's rolling a standard 6-sided die. We're going to roll this dice 3 times, and I'm going to find some probability. So when I think of rolling that dice 3 times, again, I have that dice, I roll it, then I pick it back up. And we can think about this as rolling it 3 times. Think about them as they're slots to be filled. My first row, my second roll, and my third roll. Slots to be filled, events to happen. And this is how we treat or understand the experiment. And this is what's going to help us interpret each part below. First part, I want to roll 1s on the first 2 rolls and anything other than a 1 on the last roll. So again, I'd encourage you to write out probability of, what are our events? Let me write these as slots, 1, 2, and 3. This will help us understand the event. This one's fixed, very fancy. For the first 2, I'm looking at a 1, and not a 1, right? Anything other than a 1. Now you could write not a 1, but we actually have better terms for not a 1. Instead, we can write that as 1 complement equals. Now look, before you go and break this thing up, which we are going to do, it's important to understand why we break things up. Again, this is like in consequence, 1 and, write it over here, and 1 and not a 1. So we are going to be using multiplication to break this up, little star though, because we need to be careful if we have independence. That's a good question to ask. Again, think about the question when we pick up this dice. Do we have independence? Well, the short answer is yes. But let me get to why. It's because every time I pick up that dice, the fact that I rolled the 1 initially, while I pick up that dice, it's a fresh every time. These events are independent of each other, which is good for us. It simplifies our process significantly. So I can write this then as the probability that I get a 1 on the first roll times probability I get a 1 on the second roll times the probability that I don't get a 1 on the last roll. And now I can look at each of these events separately. This is going to be a throwback for you. If we want to find the probability that we get a 1, we can always look at this as a fraction. Again, how many I want up top divided by how big my space is. Well, for a dice, I can write this as my first event here times my second one. For a dice, my space comprises of the 6 different options on a dice. And then we ask the question, how many 1s are there? Well, there's just 1. 1, 1. And so 1 divided by 6 is the probability that when you roll that dice, it shows up a 1. Next up, probability to get a 1 is the same fraction. 1 divided by 6 times, here's the unique one, the not a 1. What's the probability that when I look at that dice, it is not a 1? Well, the space stays the same. There's still 6 options to choose from. But if I want not a 1, there are 5 not 1s, namely the 2, 3, 4, 5, and 6. 5 options. So if I multiply this together, I should actually get a nice number of 0.0231. To maybe put that into a perspective, you can think about that as roughly 2%. So what's the probability? Unlikely, don't count on it. I want to write a big circle over here, and you'll see why in a second. Big circle, because we're going to talk about a very similar event, and that's rolling exactly 2 ones. Rolling exactly 2 ones. Well, wouldn't that be exactly what we talked about before? A 1, and not a 1? This is exactly 2 ones. So how are these two different? Big circle over here, 2 to compare them. Well, one thing that's very important for our first one, notice they were very precise. They said, I want 1s for the first 2, and then the last roll can be anything other than a 1. There was a strict ordering here in the way that things had to play out. And for part B, though, there is no mention of order. Well, to that end, this event, 1, 1, not a 1, is good, but it's not everything that satisfies this given experiment. And so this is certainly fine, 1, 1, not a 1, but I can manipulate, I can move this not a 1 over. Let me write over here, or we'll see why it's important later. 1, not a 1, and 1. This event is different, right? Especially if I looked at those dice that I rolled, but it satisfies the given condition. So this is certainly 1, 1, not a 1 is good, or 1, not a 1, 1 satisfies that exactly 2 ones. There's another event that's similar. Again, I encourage you to be methodical about it. This is very similar to when we built sample spaces earlier. We moved that not a 1. It should be not a 1, and then 1 and 1. And then we need to think to ourselves, is that all of them? Are there any more orderings? Can I move them around? You might be tempted maybe to move this one and switch it with that one, but that's just ones. There's no different ordering involved there. It's still a 1 and a 1. So that's it. There are 3 different orderings. Notice I use the word or. Whenever you read that, you should be thinking, I know what to do. I'm going to add up all of these probabilities together. So let me write it like this. The probability that we roll exactly 2 ones is equal to the probability that we get 1, 1, and not a 1, plus the probability that I get a 1, not a 1, and 1, plus the probability that I get not a 1, 1, 1. This probability we did earlier, it was the one above. And so this probability we know is going to be 0.0231, but here's the catch. Notice if I go into this multiplication trick over here, if I was to swap that 5 divided by 6 and 1 divided by 6, which would be the second event, I'd get the same answer, 0.0231. And so in fact, these separate orderings are all the exact same probability. So I'm just going to add this number up 3 times. We talked about exponents before. If I was to add up the same number 3 times, that's the same thing as just multiplying by 3. 3 times 0.0231, where this 3 is simply the number of orderings that we have for this event. 3 times that 0.0231. And we'll get a final probability, here we go, of 0.0694. And that's our probability that we'll get exactly 2 ones in any order. So it's very important. In fact, that's why I'll write it in circles. We'll start over here. Then when working this independence, that we ask ourselves the question, can I rearrange? Can I get a different ordering? Let's try this next one. Rolling exactly 1, 1. And so it's important when we're thinking about these events to write out what that event is. I want exactly 1, 1. That means I need to roll a 1. This is my first slot to be filled. And then I want not a 1 and not a 1. So let's find the probability that this event occurs. Probability of 1, not a 1, and not a 1. Just like before, whenever we're seeing and, these things are happening in consequence, we should think multiply, provided that things are independent. So I'm looking at the probability that we get a 1 times probability that we get not a 1 times the probability that we get not a 1 again. So this is then going to equal, for the first, we already talked about it, that should be 1 divided by 6 for the probability that I get a 1, times not a 1. There are 5 not 1s divided by 6, times 5 divided by 6 for that not a 1. This probability, if we do it correctly, should give us 0.1157. But the big question is, before you box, you should ask yourselves, can I rearrange this event? That's very important to ask before we box. And the short of it is, and some of you may have seen this when I wrote the event earlier, that it just says exactly 1, 1, meaning I don't have to get the 1 first. I can get it next. And so when I think about the ordering, I can get what I got, 1, not a 1, and not a 1. Or, important word there, let me move this 1 over. Let me get it in between. That would be I get not a 1 first, 1, and not a 1. Or I can get not a 1, not a 1, and 1. And that is all the orderings. There's no more moving around that I can perform here. So for the probability of getting exactly 1, 1, I can do so right here. There are 3 orderings. Again, the number of orderings times my original probability. Because again, the probability that each of these separate events happen on their own is 0.1157. So I can multiply these two numbers together, and you should get an ultimate probability of 0.3472, almost a third chance that I will get exactly 1, 1. And so again, very important to always ask ourselves to come up with the event, whatever it may be. I'd encourage you to think of slots being filled. And once we have an event, find the probability and then ask ourselves, can we reorder? Is there any way we can rearrange the numbers? And if they're nondescript, again, over here, no mention of order, the word we're looking for, these are permutations. We can figure out all the different permutations and then multiply by the numbers of orderings. Let's continue. Rolling 1, 2, and 3 in exactly that order. I'll dispatch with formalities here. When I'm looking at rolling a 1, 2, or 3, that's me rolling a 1 and a 2 and a 3. Each of these separately. Just like before, we have and, we multiplication, and since they're independent, that's the probability that I get a 1 on my first roll, times the probability I get a set 2 on my second roll, times the probability I get a 3 on my third roll. I have these 3 events together. If I want to find their probability on their own, we think of fractions. This is the probability I get a 1 times the probability I get a 2 times the probability I get a 3. This is going to be goofy. So when I think of the space, well, for this 6-sided dice, there are 6 options in total. How many 1s are there? There is 1, 1. For the 2, what's the probability that when you roll a dice, it comes up 2? Well, there is 1, 2 of the 6 options. So 1 divided by 6. Maybe you can see the pattern. What's the probability that when I roll that dice, it comes up a 3? Well, there's only 1, 3. And so all of these events, although different, have the exact same probability, 1 divided by 6. So if you multiply these two, all these 3 together, you should get 0.0046. Not likely, probably not going to happen. But what if the wager or the bet says, look, anything goes. As long as I get a 1, 2, and a 3 in any order, then that's certainly fine. This is going to up the probability quite a bit because to the first example, there's an order. The second one, there's no order. The second one, there's no order. So how can I work this probability? Well, just like before, the event looks similar of 1, 2, 3. But I need to think of how many permutations there are, or you can think about how many orderings, manipulations I can do. Again, this is very similar to sample spaces that we've talked about in the past. Let me be methodical here and take this 3 and swap it with the 2. So I'll get 1, 3, 2, trust the process. Watch this. If I take the 3 again and I switch it with the 1, now I'm left with 3, 1, and 2. Interesting. So the 3 kind of took its course. Let me do the same thing, moving things around, but let me do so with the 2, and I'll swap it with the 1. Let me write it down here. That's going to be 3, 2, 1. Well, that's a fun one. Or let me continue the process with the 2. 2 has not finished its journey. Swap the 2 and the 3, and I'll end up with 2, 3, and a 1. How strange. So that had its journey. The 3 did, the 2 did. Hey, the 1's over here. Let me do the 1 as well and see what that journey looks like. Move the 3 and the 1. Let me replace those. Sorry, we're over here. Then I get 2, 1, and 3. Now you might be tempted to continue the trend, right? 3 had its journey, 2 had its journey. Well, if I continue that journey with the 1, swap the 2 and the 1, well, look what that's going to lend me. Whoop, all the way back to the beginning, 1, 2, and 3. This strategy is a nice technique in order to figure out all the permutations of a certain group or ordering. You just take the last number, move it all the way through, and so on and so forth. You always get all the orderings. So how many are there here? There should be a total of 6 orderings, or 6 different ways to get exactly the same probability up here, right? All these events have the same probability. I'm going to add them together. So the probability that I get a 1, 2, a 3 in any order is going to equal, little line here, how many times I can reorder exactly this probability, 0.0046. And it looks like there are 6 different orderings. So if you multiply these two values together, we should get an answer of 0.0276. We did increase our odds significantly, but we're still only looking at 2 or 3%. Not likely, don't count on it. Let's up the ante a bit. And instead of dealing with these nice numbered outcomes, let's see about the probability of getting only odd numbers. So I'll write like this, probability of, and let me leave it blank for a second. Remember earlier we talked about that we need to think about these as 3 slots to be filled. The first one, the second one, and the third one. And it's very important that when you're finding this probability, that when you're filling these slots, you are as generic or general as possible, right? We don't want to be too specific because then we have all these different events to figure out and calculate. Let me show you what I mean. For instance, if I'm getting only odd numbers, we could say, well, look, I could get a 1, 3, and a 5, right? Those are only odd numbers, and I could find the probability. But a problem with that specific event, I mean, for one, we're going to have ordering issues, right? I can manipulate and move around the 1, the 3, and the 5. We don't want to do that. Additionally, I can get another event, which is also only odd. I could get a 1, and a 3, and then find its probability. Again, all of these satisfy the 1, 3, and the 5, all the different orderings, 1, 1, and 3. Oh no, 3, 3, and a 3. We are being way too specific. So we want to be general, back up a bit. Okay, let me think about this. I have these 3 roles to still calculate, my first one, my second one, and my third one. But instead of being so specific as to get 1, 3, and 5, let's say, let me be as generic as possible. For the first role, I'm just hoping for an odd number. So that's all I need to worry about. For the second rule, an odd number. And for the third, also an odd number. And the beauty of tackling the problem generically like this, or non-specific, is I can find out, since we have a dependence, what the probability of me getting an odd value for one rule, multiplied by the probability I get an odd for the second, times the probability I get an odd for the third. Again, beauty of independence, instead of me looking at this very complicated event, I can separate and look at these much smaller events. And so let's tackle one of them, and then we can multiply it 3 times. Equals, well, for an odd number, again, the fraction stays similar, that there are 6 different options to choose from. And I want to know how many odd numbers exist out there. Well, fortunately for you, I listed them right up here, 1, 3, and a 5, and those are all the odd numbers. There are 3 odd numbers to choose from, the 1, the 3, and the 5, 3 of them. So that's then going to be times 3 over 6 for getting an odd for the second roll, times 3 divided by 6 for the next. And so if I multiply these all together, I should get a probability of 0.125. For reference, that's actually just 1 divided by 8. It simplifies quite a bit. 1 divided by 8. Because each of these, 3 divided by 6, is just 1 divided by 2. And if you multiply 1 divided by 2 3 times, yeah, you get 1 divided by 8. That'll come up in a minute, so that's why I want to reference it now. So that's the probability that we get all odd numbers. Let me do this one pretty quickly here because it's very, very similar, and that's getting only even numbers. Notice the situation is relatively the same. I'm looking at getting an even number my first response, even my second, and then even for the last, being as generic as possible. The probability looks the same, so let me speed through real quick and evaluate it. So we get the exact same probability because the situation is the same, right? When we look at even numbers, there are 3 of them. There's 2, there's 4, and there's 6. There are 3 even numbers. And so the math works out the same, even though it's a completely different event. Now, look, the reason we did those 2, odd and even, is it's going to help us out with this maximum level difficulty question. And that is, look, I want to get some odd and some even numbers. Okay, this one's tricky because this is what I'm looking at. When I think about the event, again, we want to be as generic as possible. Well, I could get an odd number for my first response and then get 2 evens and find that probability. That's some odd and some even. Oh man, but a problem with this is I then have to think about the ordering, right? I can swap the odds with the evens. Oof. Additionally, all right, or over here, I also could get odd, odd, and even. And then I have to find that probability. Okay, this is ballooning quickly because I got to find this first one, find the ordering, multiply, and then do the second one, multiply. Okay, this is getting silly. Maybe there's a different way, a more efficient way to do it. And it looks like this. I'm going to use this little trick here. Let me first write out the probability. I want to get some odd and some even. There's a very nice trick or formula that we had in the past. So let me write that formula here. And it's the probability of doing something is equal to 1 minus the opposite of doing something is the probability of doing nothing. So let me see if I can apply that to this little trick, this little formula that we have over here. So let me write this as equals to 1 minus the probability that I get for something to happen, some odd, some even. It's like a mixed bag. I want no odd and even, or no even and odd. So it's the probability of then getting only odd or only even. So when we talk opposites, this gets into a little bit of probability and truth logic rules, but the opposite of and is or. And then so we're looking at some odd, then we want only odd, some even, only even. And so this is the opposite or the complement of getting some odd and some even. This is going to unleash something beautiful here. So look, I can write this as equal to 1 minus, whenever we see or, we should have this impulse to add things together. We called it the addition rule, and it looked like this. Let me write brackets here to highlight that we're working inside this. This should be the probability of getting only odd plus the probability of getting only even, and then minus their overlap, the probability that I get only odd and only even. Again, that was the addition rule that we had in the past. Ooh, here we go. This is where it's going to line up together. 1 minus. Well, if the probability of getting only odd, that's what we just talked about above, is 0.125 plus the probability of getting only even, again, evaluated just above, 0.125 minus, this one's kind of goofy. What's the probability that when I look at 3 dice, that they are only odd and only even? I think we have a name for this type of event, and we call them mutually exclusive, that they cannot happen together. I can't get only odd and only even at the same time. It's impossible. Probability is 0. And so now I can finish my probability. It should look like 1 minus, if you add 0.125 plus 0.125, you'll get a quarter, or 0.25. And so my probability will finish out to be 0.75. Actually pretty likely. If I want to write that as a percentage, that would be 75% chance that when I look at these dice, they'll have a mixed bag, right? Some odd and some even, that we avoid the extremes of getting only odd and only even. And so again, these formulas, these tools that we have, I like to call chapter 3, the wild, wild west of probability, because it is. It's all of these rules and tools, and then we figure out how they line up together. Oftentimes, our best bet is to have the rules at our disposal, and then to try to reason our way into them to say, okay, this event's very difficult. How else can I do? And complements is a good way to get that. Again, you don't have to do the probability. You'll get the same answer if you do the probability that we talked about earlier over here, where you look at odd, even, even, find that probability, do some ordering, and then you multiply that by odd, odd, even, do the orderings and add that. And if you add those two probabilities together, boom, you'll get the same answer, 0.75. It'll just be a little bit messier. It'll probably take more space than I've allotted here. Many different ways to get the correct answer. This one's a bonus because it relates to what we started off in the very beginning. When we first introduced probabilities, we said, hey, there's an origin story of where some people say that probability began. Let me read it and then we'll solve it using the tools that we learned here. So if you remember our historical gamblers' dispute between those two famous mathematicians, and we had this game. This game consists of throwing a pair of dice 24 times and determining to bet or not on if you'll get at least one double sixes, or I'll write that as D6 for short, double sixes. So you got 2 dice, I'm rolling them, I'm rolling them, I'm rolling them, I'm rolling them 24 times. And the question is am I going to get at least 1 double six? Or better yet, should we better not? That is the big question we're trying to answer. So let's see if we can find the probability, right? What's the likelihood this will occur? And that'll inform our decision. So let me first start off with writing what probability we're interested in. I'm looking at the probability that we get at least 1 for shorthand, I'll write D6 for double six equals. We got a lot of fancy rules. One thing, whenever you read at least 1, you should have this impulse to say, look, at least 1, I'm going to think 1 minus the probability that I get none. Again, at least 1, think 1 minus none. I want none double sixes. Again, the grammar doesn't work, so let me write no double sixes here to make the grammar work. But the rhyming works better if you write at least 1, 1 minus none, so that's why I stick with it. Interesting. All right, so this is going to be equal to, that should be 1 minus, so that means I want no double sixes, but I'm doing this roll 24 times. That's how many times I'm repeating this experiment over and over and over. So if I was to write this out in the big complicated event that it is, it would be, I'm interested in the probability that I get no double sixes on the first roll. On the second, let me do a little ellipse all the way on the 24th roll. This is one big event that we're interested in. So if I want to think of a way to express getting not a double six, well, again, you could say not double six, or I could write double six complement, and that represents the event that is not a double six. So I want not a double six and, to write a little arrow here, and, or maybe a little comma, not a double six for the second roll, comma, little ellipse, because we're doing not a double six, not a double six, not a double six, 24 times, not a double six. Here we go. This is where the magic starts to come into place. Well, notice I'm looking at all of these, not a double six and, not a double six and, stressing that word very importantly, because I'd like to do multiplication, but very important, we need independence. If independent, we can only do the multiplication if they're independent. So the question is, are they? Well, notice we're rolling a dice, right? We're picking that thing up and rolling it. It's a fresh every time. Every time I pick those dice, it's a new day, a new roll for us. And so, yes, they are independent. Yep. Beautiful. So now I can separate this. Instead of looking at this as one big event, 24 rolls, I can look at this on their own. So this will be the probability that I get not a double six times the probability that I get not a double six times little ellipse, because we're going to look at that 24 times probability to get not a double six for the first, for the second, and all the way to the 24th rolling of these 2 dice. Whew. Let's see how this cleans up. So now that we've separated this complicated event to smaller events, this is going to balloon and then it's going to clean up. So 1 minus, I want to know what's the probability that I get not a double six. Again, whenever we're doing probability, I can always write this as the number that I want up top, divided by how big my space is below it. And then I'll just write a little wiggle line for the rest. So how many items are that I want divided by my space down below? This is where this table is going to come in handy. So this should be 1 minus, how many do I want? Notice in all my responses, there's snake eyes for us. Not that that's needed, but it's nice to know. If I look down here, whoop, this is the double six. This is what I not want. This is what I don't want. Do not want. That's what I want to avoid, right? I want the complement, not a double six. So how many items are that I want? Well, there are n equals 36 options in total. That's how many pairings there are. 1, 2, 3, 4, 5, 6 times 6 columns. So 36 altogether. That means there are 35 outcomes that I'm fine with, that are perfectly good for not a double six out of the 36 in total. So 35 divided by 36. That's for me rolling 1 time though. So I need that multiplied by 35 divided by 36 for the second roll, times, this keeps going, and you have 24 of these things, 35 divided by 36. Holy moly. All right. So if you'd like, you can get a calculator out and write 1 minus 35 divided by 36 times 35 divided by 36 times. Okay, this is goofy. Instead, let's think of a more efficient way to write this with exponents. 1 minus, let me write parentheses over here, 35 divided by 36, and I'm multiplying that thing 24 times. Again, if you need to type that, that would be a little caret symbol. Caret 24. And we should get probability, little arrow signs over here, we should get 0.4914. That is my probability that we're interested in. If I want to think about that as a percentage, let me round it to 2 decimals and write 49% chance, right? That relates to, they want to know, what's the probability that we'll get at least one double six? Well, it's not quite 50%, but it's pretty darn close. 49% chance that we'll get at least one double six. And so let's see if we can answer the question. Again, the question was, should you bet or not bet? Again, that this will occur, that you'll get at least one double six. This is the question, should you bet or should you not bet? That was the big question to answer. Well, again, if it was 50-50, then it's like, hey, no recommendation, do whatever you want to, but we're just under that bar. So should we bet? Nah, not a safe bet. It's a little bit under 50, but certainly you're playing the odds at this point. It's very close to 50-50 that you'll get at least one double six out of rolling the dice 24 times. Chapter 3 really is the wild, wild west of probability. So let me wrap with this. We have a lot of rules and formulas that we get when we compute probability here. We're arming ourselves. We have addition rule. We have multiplication rule. We have this mutually exclusive and independence. Those are important for us. But notice this multiplication rule comes with a huge caveat, and that's that we need independence. And so oftentimes it doesn't work with questions that we're maybe picking up cards. You have 5 cards in your hand, because every time I pick up a card, I don't put the card back. I'm holding it, and then I pick up another one. And so those events aren't independent. I cannot use this particular multiplication rule with those. And so we do have some tools. We have an arsenal way to calculate, I think, some pretty complicated events, but the story is not finished. We have another more generic formula that we can get, and we'll talk about that one in the next one. So let me close with this. If you enjoyed the video, I appreciate the time you put into it. If you didn't, I apologize. All right, for the rest of us, I'll see you in the next one.